Every time you fill up your car, you're holding the result of a story that began hundreds of millions of years ago. Gasoline isn't just a liquid. It's the product of nature, time, and science combined. To truly understand how it's made, we need to go back to the very beginning, long before humans even existed. If you like similar educational content, please like, subscribe, and share the video with your friends. Hundreds of millions of years ago, the Earth's oceans were full of microscopic life, plankton, algae, and plants that absorbed sunlight and carbon dioxide. When these organisms died, they sank to the bottom of ancient seas and were slowly buried under layers of sand, clay, and rock. Over millions of years, under extreme heat and pressure, this organic material transformed into a dark, dense, carbon-rich substance, crude oil. Trapped beneath impermeable layers of rock, crude oil gathered in underground reservoirs. For ages, it remained hidden until humans learned how to reach it. Today, towering steel rigs drill thousands of meters into the earth, piercing rock formations to tap into these ancient deposits. When pressure is released, the thick black liquid bursts upward, often mixed with natural gas and water. But crude oil on its own isn't gasoline. It's a chaotic mix of hundreds of different hydrocarbons, some as light as gas, others as heavy as tar. To turn it into something useful, the oil must go through an extraordinary transformation. A journey inside one of humanity's most complex creations, the oil refinery. Inside the refinery, crude oil is first heated to extremely high temperatures. The heat causes it to separate into layers or fractions based on boiling point. At the top of the tall distillation tower, the lightest vapors condense into gases and gasoline fractions. Lower down, kerosene, diesel, lubricants, and heavy oils form. The very bottom holds the thick residues that will later become asphalt and bitumen. Among these layers lies one of the most valuable, the gasoline fraction. This fraction is the starting point, not the finish line. It still lacks the stability, volatility, and purity required for modern engines. The refining process has only just begun. Once the crude oil has been separated into its different fractions, the real transformation begins. This is where raw, ancient hydrocarbons are reshaped into the powerful, clean-burning fuel that keeps millions of engines alive every single day. The gasoline fraction coming out of the distillation tower is still far from ready. It's only a rough, unfinished material. To become true gasoline, it must be rebuilt on a molecular level. And this happens through some of the most advanced chemical processes in modern industry. The first major step is called cracking. The name is fitting, because that's exactly what happens. The long, heavy hydrocarbon chains are literally cracked into shorter, lighter molecules. Inside huge reactors operating at temperatures of around 500 degrees Celsius, the oil is forced to break apart. In modern refineries, this doesn't happen randomly. Pulverized catalysts, special materials that speed up reactions, swirl inside these reactors, guiding the breakdown so that lighter, more energy-rich molecules are formed. This process, known as fluid catalytic cracking, is one of the essential engines of gasoline production. But cracking alone doesn't shape the molecules into the right forms. Engines need fuel that burns smoothly and predictably, without exploding too early under high pressure. That's where reforming comes in. Reforming rearranges the structure of hydrocarbons, taking simple straight chains and converting them in touring-shaped or branched molecules. These structures burn more evenly and resist premature ignition, the key to raising the fuel's octane rating. The higher the octane, the better the engine can perform. Another crucial process is isomerization, which takes linear hydrocarbons and reforms them into branched versions with improved stability and combustion properties. Together, reforming and isomerization give gasoline its characteristic smooth burn and protect engines from the destructive knocking sound caused by early ignition. Alongside these processes works hydrocracking, which uses hydrogen under high pressure to break down heavier fractions even further while removing impurities like sulfur and nitrogen. This hydrogen-rich environment produces extremely clean and high-quality blending components. Removing sulfur is especially important. Sulfur compounds can damage catalytic converters and create harmful emissions if left in the fuel. Once these processes are complete, the refinery ends up with dozens of different streams of hydrocarbons, each with unique characteristics. To make finished gasoline, engineers have to combine them with almost artistic precision. This step is known as blending. The goal is to create a fuel that meets very specific standards: the right volatility for cold starts, the right octane for efficient combustion, the right stability for long-term storage, and the right emission profile for modern engines. But blending isn't only hydrocarbons. Modern gasoline also contains additives designed to protect engines and reduce emissions. Detergents keep injectors clean. Antioxidants prevent the fuel from degrading during storage. Anti-corrosion agents protect fuel systems. Anti-foaming agents improve the filling experience at the pump. In many countries, refiners also add a controlled amount of ethanol, which increases octane and reduces overall carbon intensity. By the time all these processes are complete, the fuel has been sculpted into something incredibly refined. A precise chemical tool designed to deliver the perfect balance of power, efficiency, and environmental safety. When gasoline finally leaves the refining units, it still has one more enormous challenge ahead. It must prove that it meets every strict standard set by engineers, regulators, and modern engines. Before a single drop can be sold, it enters a world of laboratory testing that is just as intense and controlled as the chemical processes that created it. Every batch is sampled and analyzed with remarkable precision. The most familiar measurement to drivers is the octane rating, which tells how well the fuel resists premature ignition under pressure. But in the lab, octane is not simply a number printed on a pump. It's measured using specialized test engines that simulate extreme conditions inside real combustion chambers. Higher octane means the fuel burns smoothly, evenly, and powerfully without knocking, allowing modern engines to run efficiently and with more compression. But octane is just one piece of the puzzle. Gasoline must also have the right volatility, a measure of how easily it evaporates. When temperatures are low, the fuel must evaporate quickly enough to help the engine start. But at high temperatures, it must not evaporate too fast, or vapor bubbles can form in fuel lines and disrupt engine performance. This delicate balance is tested and adjusted continuously. The fuel is also checked for sulfur content, which must be extremely low. Even a small amount of sulfur can contaminate catalytic converters and create harmful emissions. Modern regulations require sulfur levels to be reduced to just a few parts per million, and refiners use advanced hydrotreating to meet these standards. In the lab, devices measure sulfur down to micro-level quantities, ensuring every shipment is as clean as possible. Another critical test involves stability. Gasoline can degrade over time, forming gums and residues that clog injectors and disrupt combustion. To prevent this, the laboratory exposes the fuel to heat, oxygen, and time, then measures how well it resists oxidation. Additives are fine-tuned to improve its shelf life and protect engines during long periods of storage. Once all tests are passed, gasoline flows into massive storage tanks, sometimes holding millions of liters. From here, it enters a vast logistical network, pipelines stretching across countries, rail tankers carrying thousands of tons of fuel, and tanker trucks that refill stations every day. At distribution terminals, gasoline may receive additional local additives required by regional laws or climate conditions. Every shipment remains traceable. Modern tracking systems record where a batch came from, when it was produced, and where it is delivered. Even at fuel stations, inspectors periodically take samples to ensure the gasoline hasn't been contaminated or diluted. This guarantees that the fuel you pump at midnight on a remote highway has the same quality as fuel sold in major cities. Gasoline's journey from deep within the earth to the fuel pump is staggeringly complex, a chain of science, engineering, logistics, and precision. And the moment it reaches the pump, the final stage begins, transforming its chemical energy into motion. When gasoline finally reaches your car's tank, it has completed one of the longest industrial journeys on Earth, but its most important transformation is still ahead. Inside the engine, in a space no larger than a fist, gasoline turns into power, heat, sound, and motion. And it all happens thousands of times every minute. As the engine runs, gasoline is injected into the combustion chamber and mixed with air in an extremely precise ratio. Then, in a fraction of a second, the spark plug ignites the mixture. Hydrocarbon molecules break apart and combine with oxygen, releasing heat and expanding gases. This sudden burst of pressure forces the piston downward, rotating the crankshaft and generating mechanical energy. What was once ancient organic matter, plankton and plants buried millions of years ago, becomes the force that moves a modern vehicle forward. But burning gasoline also releases emissions, especially carbon dioxide. Even though modern engines and catalytic converters drastically reduce harmful byproducts like carbon monoxide, nitrogen oxides, and unburned hydrocarbons, the fundamental chemistry remains the same. Carbon stored in ancient oil returns to the atmosphere. This is why gasoline sits at the center of discussions about climate change and the transition to cleaner energy. Yet the story doesn't end with gasoline as we know it today. Scientists and engineers around the world are developing synthetic fuels, produced from hydrogen and captured carbon dioxide using renewable electricity. These fuels could one day offer the same convenience and energy density as gasoline while being nearly carbon neutral. Meanwhile, research into cleaner refining processes, advanced additives, and new combustion technologies continues to reshape the fuel landscape. At the same time, the broader energy system is evolving. Electric vehicles, hydrogen engines, and hybrid technologies are rapidly advancing. Modern refineries are transforming into integrated chemical hubs that no longer rely solely on crude oil. They recycle plastics, convert waste into energy, and develop low-emission fuels that can power airplanes, ships, and heavy machinery. Still, gasoline remains one of humanity's most transformative inventions. It powered the rise of modern transportation, enabled global trade, and shaped the world's cities. It represents a bridge between the ancient past and the technological future, a substance born from oceans that no longer exist, refined by chemistry and unleashed in the cylinders of millions of engines. The next time you press the accelerator and feel your car surge forward, you're experiencing the final step of a journey that began in prehistoric seas and passed through the most advanced technologies ever built. Gasoline is more than fuel. It's a story of Earth, time, and human ingenuity, condensed into a single drop of shimmering liquid.